So let me just say good morning, everybody. Welcome to Saturday Morning Astrophysics at Purdue. It's nice to have you here this morning on a topic that I think is interesting to me and should be interesting to you as well. Sizing up the universe, pretty broad topic. So when we talk about the universe, what comes to mind? I'm asking the students, not the TAs. Anybody want to put something in the chat or unmute yourself and tell us what comes to mind to you when we introduce the universe? What is the universe? I don't know. Well, tell me. Who's got an idea? What is in the universe? Somebody tell me that. What's in the universe? What does the universe consist of?
Any answer you give will be correct to that question.
Okay, so I'm seeing some things here. The solar system, our solar system, uncountable other solar systems, time, space, energy, matter, anything you say, that's the universe. How far does it go? We don't know. Is there only one? We don't know. It's it's a scientific question. It's a philosophical question. It can be a spiritual question because some cultures around the world think of the universe as some part of a spiritual existence that can extend beyond what we see and know. And I don't know when I go there. I don't know anything about that. But fascinating topic. So let's just dive into the session, and I will introduce our guest speaker for today, our presenter, Professor Paul Duffell from Purdue Department of Physics and Astronomy. So, Professor Duffell, are you live and ready to go?
I think so. Thanks, Dave. So let me actually before what we'll be doing today is basically doing a similar exercise that Hubble did back in the 20s, so Hubble was the one that basically discovered that before Hubble, it was thought the universe was basically a static thing, like there were stars that just sat there in space, and the only reason the sky changed was because the Earth rotated and went around the sun, and we all just thought the universe was just a static thing, but Hubble was able to show that it's not, that it's an evolving thing that has been expanding throughout history, throughout the age of the universe. That the universe may actually have an age, and that these things, but the universe is evolving in time. And so the way he showed that is with an exercise we'll do today. We have a little bit better data than Hubble had back in his day, so our exercise will be a little bit easier than his was. But I can show you the data that we're going to be looking at. So what I'm going to do in order to do that is I'll share my screen and show you, because of this first slide I have the data. So what we're looking at is a plot. And basically, all of the labels hopefully tell us all the information we need to know about the plot. The title of the plot says recession velocity of distant galaxies. So each point on this plot represents a galaxy. The data you got sent doesn't have error bars on it, so sorry about that. My data does have error bars, so it looks cooler. So each point on this plot is a galaxy, and in order to understand this plot, we can look at sort of the different axes of the plot. So on the x-axis, we have the distance to the galaxy. So each galaxy, this is, and the distance is in this funny unit here, megaparsecs. Anybody heard of megaparsecs? All right. Well, if you haven't heard of parsecs or megaparsecs, mega would mean a million. So megaparsec is a million parsecs. But it's just a really big distance, if that helps. So Hubble was looking at the distance to a whole bunch of distant galaxies, and he was looking at their distance. The other thing he was looking at was their velocity. And the velocity is the y-axis here, and it's also in units. It's kilometers per second. So immediately you can see these galaxies are moving, like even if they were 1 kilometers per second, that feels really fast, right? But these are moving at tens of thousands of kilometers per second. So these galaxies are moving fast. And if you notice, it says recession velocity. They're all moving away from us. Now, not every single galaxy is moving away. There's a couple very nearby ones that are not moving away from us. But basically, any galaxy, other than those few that we look at in the universe, they're all moving away from us. And Hubble noticed this and thought it was kind of crazy. But then he basically plotted all their velocities and their distances, and a plot sort of like this, except his data wasn't as nice as ours. His data was also much closer galaxies, so they would have been this tiny little region down here around 100 megaparsecs. So we have a lot nicer data to work with. But the idea was to understand what he basically discovered with a plot like this was to show that the universe was expanding. And so that's what we're going to show today, and understand how the universe expanded and how it got to be where it is today.
Yeah, so once you select your data, and you can do that by clicking these top two columns and kind of drag your mouse across so that both of them are completely selected. We have 58 or 57 data points in this case. So we have a distance and a velocity associated. Each one of those would be associated with the galaxy. So each row in there. And then you go to insert. And from here, we need to make that XY plot, that XY scatter plot. So there's a button over here next to the big icon that says recommended charts. And you can click on that and just select the first option. And it will create a plot based on the data that you selected. Does that make sense to everyone? Is that clear? Cool.
So in Excel, one column will be one axis, the other column will be the other axis. One is X, one is Y.
Right. The leftmost column will always be your X, which is how we know that it's distance, as Maura pointed out earlier. And then the right column will be your Y-axis. In this case, it's velocity. So yeah, then we want to rename our title because it arbitrarily threw in the second column as the title, the second column name. And as Professor Duffell went through, this is recession velocity of distant galaxies. For the essentials, everything that you need is going to be in chart elements. Add chart elements up here in the top left. And from here, you can add in axis titles, which are always important for knowing what each axis is. So you have your horizontal and your vertical. And we went through this earlier. The y-axis is our velocity, which is in kilometers per second. And then our x-axis is a distance in that megaparsec. In order to get Hubble's constant, like I said, we need the slope of this, of our data, the slope of a trend line that we're going to put in. And you include it in exactly the same way that we just included our axis titles. It's on this add chart elements. And in this case, our data is linear. For this purpose, all we really need is the equation that this line is made from. So for slope, y equals mx plus b, that's what this equation is. And then m being our slope is 62.353, which is what we're going to use for the value of h.
Sorry, so slow down. I wasn't in the room. Did we clarify why we have this equation, y equals something times x plus something, right? Did we cover like that, do we understand the equation of a straight line? So this tiny equation here, y equals 62 point something x plus some number. Why is that a straight line? Or is that something we've seen in math for a straight line? Okay, head nods. All right, so good. So what would you call it? Yes, good. So Matthew says y equals bx plus m, although that's not usually how we write it, or that most people use m, swap those two letters around. They'll say y equals mx plus b. But those are two constants that describe that sort of parameterize your line. Y equals mx plus b. So what do the m and b stand for? Yeah, good. So what do the m and b stand for in that equation?
M is the slope and b is the y-intercept.
Okay, great. So Good. So now it might be tempting to say, okay, all we want is the slope, but we should stop and say, what should this y-intercept be? Well, how would I interpret the y-intercept? In general, what does the y-intercept mean?
It's the y value when x equals 0.
Okay, good. So x equals 0. So all these galaxies of different distances, what would distance equal to 0 mean? How would we interpret the y-intercept? What galaxy should that be?
Would it be ours?
That's our galaxy, right? On the x-axis it's 0, distance of 0. That's our good. Yes, exactly. That's our galaxy. And so, what velocity would we expect for that one? So we're looking at all these different galaxies, and we're measuring. They're all moving away from us with some velocity. What velocity should we say is our galaxy's velocity?
Matthew put in the chat 0.
Oh, good, excellent, exactly. So at least from our frame of reference, our galaxy is stationary. The other ones are moving away from us, right? So that means our y-intercept is what? Yeah, you just had to say the same answer again. Exactly. 0. Right. Okay, good. I want to make sure that'll change your answer. So I want to make sure you take that into account.
And if it wasn't clear, Hubble's constant is the slope that we measured.
Yes, thank you.
So that's what we're trying to think about the units here. And a little hint is to think about what we actually made to figure out the slope. What units did we already have?
Matthew McKinnis says kilometers per second over megaparsecs. Does anyone agree with that? I see maybe nodding heads. Does anyone, any reaction, thumbs up from other people or thumbs down? See a thumbs up there. Okay, yes. So yeah, exactly right. So we took our rise over run, and I'm going to actually share my screen from my iPad and pull up a whiteboard that we're going to go through this together. So everyone has their worksheet pulled up, I presume. So remember from our slope, we calculated h to equal, remind me of the number, 63, 62.35. 0.35. Yep, 0.353. And then we said that was kilometer per second over megaparsecs. Does that look good to everyone? Okay. So there's a second question on there, and we want to use this value to estimate the age of the universe. We know from the worksheet that the velocity you can calculate using h, and I'm going to use, for my purposes, for multiplication, I'm going to use this dot, h times d, h times d. So what's v in this case and what's d? Can anyone tell me?
Velocity and distance.
Yep, so exactly. So we have velocity and we have distance. If there's at any point you don't know what I wrote or you can't read my handwriting, please let me know and I will rewrite it and clarify it. But yes, our v is velocity, our d is distance. And what if we solve this for h? What does h equal? V over d, right? Exactly, Matthew. Good job. Right. Okay, so we have that information. What do we learn, or what do we know about the second equation that we have on there? So we know our Hubble's constant, we know our units, and we know that Hubble's constant is the velocity over the distance, right? So that second equation that we have on there, what does it say? D equals V times T, right? So that second equation is D equals V times T. Okay, so we know what D and V are. What's T? T represents time. And that's what we're going to use to estimate the age of our universe. So if we solve for time, what does that get us? We solve for T. T equals what?
D over V.
D over V. Can anyone see any similarities between these two?
They're inverse.
They're inverse. So what does that mean for time? Exactly. So what's another way that we can rewrite time knowing that so let me write this out. Our time equals 1 over h, which in this case is 62.353 kilometers per second over megaparsec. If you look at those unit conversions, you're going to see a lot of the units that make up our Hubble's constant are in there. So we're going to take a kind of step-by-step journey on going through these unit conversions to go from 1 over h to the age of the universe. So we're going to start. I'm just going to have us focus in on this h value. So if we write h equals 62 that was a really bad equal sign. Whoa. 62.353, and we just write kilometer per second over our megaparsec. What looks like a good way to start? What from those unit conversion formulas, what do you see in the units that we have for Hubble's constant that we may be able to convert to something? And then in our numerator, we have our kilometers per second. And then on our denominator of that is now 3.1 times 10 to the 22nd meters. Okay. Where do we go from here? What other conversion factors do we have that can help us isolate that time value, isolate this s, this seconds?
Did we multiply by 1,000 meters to convert to kilometers and then cancel them?
Right. So exactly. So we have this kilometer value, and we know that 1 kilometer equals 1,000 meters. Okay, so this one, we can write it out exactly the same way. So we have a kilometer, and you multiply conversions, and we want to get meters. That I actually rewrite this to move that seconds into the denominator to make it less confusing. So in this case, it could be 62.353 over 1,000 meters divided by seconds times 3.1 times 10 to the 22nd meters. Does anyone have a number yet?
I got 2.011 times 10 to the negative 18.
Matthew, also the same thing. So 2.01, you said? Remember?
011.
0.11 times 10 to the negative 18. What are the units that we have left, right? So we saw our meters right here. Those got canceled out. But there was something else in the denominator, right? What's left? The seconds, right? But if I write it as, this h equals 2.011, if I write a second there, is that right? Does that look right?
It's 1 over seconds.
Exactly. It's in the denominator. So be very, very careful that when that unit's left over, yes, our meters canceled out, but we still have a second in the denominator. And that's really, really important that you remember that. Why is that important? Well, let's go back to our time equation. What was our time equation again? T equals 1 over h, right? Okay, so let's substitute in our h value. 1 over 2.011 times 10 to the negative 18th, and then 1 over second. And tell me the number that you get.
I got 4.97 times 10 to the 17th.
Our time equals 4.97 times 10 to the 17th. Matthew got the same thing. Is everyone else getting that number? Does anyone else have a different answer, a conflicting answer? Yeah, Matthew, same thing. Both Matthews and Maura. What unit is this in? Remember, we have our thing here. What happens to that 1 over seconds when it's in the denominator? It becomes seconds, right? Because it flips to the top. When you have a denominator in the denominator, it's going to flip to the top. Fantastic. So that's our time. How long would it take us to count out that many seconds, right? That's not a very, very useful number for our brains to wrap around, right? It's really, really hard to quantify what that is in seconds. So there's one last conversion factor over there that we're going to use to make this a lot easier for us. So yeah, you should get something out of your calculator that's 1.6 times 10 to the 10th. And then as Matthew pointed out, both Matthews pointed out, the unit left over is years. And Matthew McInnes made a very, very great observation that, if you do the scientific notation, drag it out to however many zeros you need to, this is 16 billion years. And does anyone know how old the universe is? How old we think it is off the top of their head? Braden, what is it?
About 14 billion years. I think 13.8 is the precise number.
Yeah, so about 13.8 billion years. So yeah, this is a really, really good rough approximation.
All right, so we're back. So we had 2 different breakout rooms, so we should have 2 different answers for everything. So what do people get? First, let me just ask, what do the 2 groups get for the age of the universe? Somebody that's not the TAs should answer this.
We got 16 billion
16 billion? 16 billion what?
years.
Good.
We got 15.4.
15.4 billion years. Okay, so we got 2 different answers, which is always fun. So what did the 2 groups get for Hubble's constant?
We got 64.6.
64.6, and do you remember the units of that?
Kilometers per second per megaparsec. That's
good. Okay. And I saw in the chat somebody said the other value that they got 62.353. And by the way we're doing this, you can tell that we're using way too many decimal places, but that's okay because we're not. This is not that precise, but it's fine. Good. So we got 2 different answers. Do we have any idea why we got 2 different answers? There's a number of ways we could have gotten 2 different answers. Yeah, go ahead.
Well, in our group, we adjusted the I forgot the word for it, but the the thing for the y-intercept, because we're supposed to be like there because our velocity is supposed to be 0. So we adjusted it for that.
Right, so you remembered getting a different value of h, the slope, when you let the y-intercept be whatever value it was, but when you forced it to be 0, you've got a larger slope. Do we think, is that probably the answer? I mean, that's one thing. Another person said different rounding, which can totally change the answer a little bit too. I'll show you. This is, of course, the plot that we've all looked at. Of course, I made a plot with fun error bars because I had access to the data, so I had access to the error bars too. By the way, you shouldn't feel bad if you got different answers for Hubble's constant, because I think Hubble got something like 100 kilometers per second per megaparsec the first time he did it, because he was working with data, like a handful of data points, and their error bars were much bigger, and so he got a slope of about 100. And that's okay, so we're doing better than Sir Edwin Hubble, so I think that's pretty good. So when I did this, of course, you'll notice I did it because I knew the answer. I knew the answer was around 70 kilometers per second per megaparsec, and you'll notice that I just sort of drew a line on here that had that slope. I didn't even fit the points. I just said I know what the answer is, so I'm going to. But if you notice, like, one thing that you'll do that you would get a different answer from me is because if you do fit this, you notice that when I choose 70 kilometers per second per megaparsec as my slope, it doesn't seem to fit these distant ones very well. And so that's something that I think, well, I'll talk about in a little bit, but it's something you should think about. Why I thought that was okay, that it's not fitting the more distant galaxies. But it does actually fit these sort of closer by ones really nicely when I use that slope. And then when I did this, I said I did the same calculation you guys did with distance equals velocity times time, but I had a different value for this thing I called h naught, or I guess I called it we called it h in the worksheet, but we call it h naught also, Hubble's constant. You just take 1 over that and you get, I said 14 billion years. So I said 14 billion, one of you said 15 billion, other of you said 16 billion, and Edwin Hubble said 100 billion. So, or actually, no, he would have 1 over 100. So he would have been a much younger age that he would have predicted. So that's pretty good. But all of it is basically estimating around the same age. Go ahead, Isabel.
Yeah, sorry, I just had like one little question. Why aren't the megaparsecs like multiplying the seconds in the units for the Hubble constant? Like you could do that, couldn't you?
Sorry, what? You could, yes, that's right. So Hubble's constant, so this is, that's right. So when in astronomers, we don't like change. So when Hubble wrote this down, he wrote it in kilometers per second per megaparsec, and we've used those units ever since. But you're right, we could cancel those units and just write Hubble's constant in 1 over seconds or 1 over years. And that would be totally reasonable because that's sort of a more natural unit for it. But because astronomers also like to use units that are relating to the measurements that we're taking. So we like to, because we're measuring velocities and we're measuring distances, astronomers will often not cancel their units even though they could. But you're right. I mean, when I do calculations, because I'm a theorist, I'm not an observer. When I do calculations, I almost always cancel all those units because it's simpler to work without so many units to convert. Good. And so then. Of course, there was this last thing. The second breakout room started talking about this, but that's okay. We can all talk about this now, which is this data point here is about 720 megaparsecs, right? So that's the most distant galaxy in the sample. And so, at the end of the worksheet, we had this question, which is basically we said, we wrote this question that said the first, sort of a thought experiment. The distance, it takes light 8 minutes to get from the sun to us. This is a fun fact that you may or may not know. It takes 8 minutes for light to get from the sun to us. And therefore, when we look at the sun, we're not really looking at exactly what it looks like now. We're looking at, when we see the sun, we're seeing what it looked like 8 minutes ago. So like if the sun suddenly blew up or there was a flare on it suddenly or something like that, we wouldn't see that until 8 minutes later. So we're always looking at it and seeing what it was doing 8 minutes ago, just because it takes light that much time to travel. And similarly, the second sort of point that sort of extrapolating, if something is 1,000 light years away, so somebody say what a light year is. It's how far light travels. It's long distance, that's right. It's how far light travels in a year, which is a very long distance, but it's a convenient unit of measure because we can say if something is 1,000 light years away from us, that means it takes light 1,000 years to get to us. So if we're looking at a galaxy 1,000 light years away from us, we're not looking at the galaxy as it we're not looking at the galaxy as it is today. We're looking at the galaxy, what it looked like 1,000 years ago, because if it's 1,000 light years away from us. So then I asked this question, what about this galaxy, this really distant one, 720 megaparsecs? How long does light take to travel to us? When we look at that galaxy, we're not looking at it as it is today. We're looking at it as it was some time ago. So how long ago was that? So can someone at least tell me how you do this calculation? Yeah, Isabel.
So what we did in our breakout room was multiply the megaparsecs times like what a megaparsec is in parsecs. So that's 10 to the 6. And then times what a parsec is in light years, which is 3.26.
Right.
Yeah.
So do people understand that? So we convert from, we're basically converting from megaparsecs to light years, because megaparsec is a distance and light year is a distance. So we just have to do a unit conversion, basically. And that's all sitting there on the sheet. So you multiply by 10 to the 6 to get in parsecs, and then you multiply by 3.26 to get in light years. And can you tell me what about what you guys got for for how many light years away it is?
We got about 2.3 billion light years.
2.3 billion light years. Good. And that's what I got too. So does that make sense to people? So this distant galaxy is 2.3 billion light years away from us, which means we're not seeing this galaxy. We're not seeing what it looked like. What it looks like today. We're seeing what it looked like 2.3 billion years ago. And if you think about it, 2.3 billion years ago, the universe was a different place. How do I know that it was so different 2.3 billion years ago? Do you remember what we got for the age of the universe? Yeah, let's see what's in the chat. So yeah, 16 billion years, right? So if the universe is 16 billion years old, and this is 2.3 billion light years away from us, then that's actually 2.3 billion years is not is a decent fraction of the age of the universe. It's like more than 10% of the age of the universe is that it took light to get to us. So the further away we look, the further back in time we're looking at, and the more we're probing the evolution of the universe. So that's not something we did explicitly today, but it's something to think about, is that when we start looking at these distant galaxies, we're looking into the past, and if we look far enough into the past, we're seeing actually back in time towards the Big Bang. So I'm going to say a little bit more about that in a second. But the other thing we should think about, when we did this problem, we thought about us as sort of the center of the universe. And so I'm going to do some exercises to sort of think about when Hubble saw every single galaxy was moving away from us, you might have thought, what's wrong with our galaxy that everyone wants to go away from us, right? It makes you think that, it sort of almost revives this idea that we're supposed to be the center of the universe because everything is moving away from us, right? And so what we eventually sort of understood is the expansion of the universe is not really this motion of stuff through space. It's really the expansion of space itself. And so the sort of visual way that people like to describe it, for example, is imagining if you inflate a balloon and you have imagine these are galaxies, these points, these stars are like galaxies, and the points are not actually moving on the balloon, right? But as you expand the balloon, the space between them is growing. And so that's really what's responsible for those velocities, is that it's not that the galaxies are actually moving themselves, it's that the space itself is expanding. And so from any point on this balloon, it will look like everything is moving away from you. And so that's sort of what we've now sort of understood, and how we now interpret Hubble's results is that it's not necessarily that the galaxies themselves are all moving away from us. It's that every galaxy is moving away from every other galaxy because the space between them, because space-time itself is expanding. Let's see what I have. Oh, I have a little exercise. It's kind of fun exercise that I can show you. This I'll show you with it. So what I did here, this is to kind of illustrate the concept of expansion of space. So this is all I plotted here was just like a map of constellations. Really, I just needed any sort of kind of star map or galaxy map, and I thought this one kind of looked cool. So I took this bunch of we can actually keep doing this in the thing, but I'll show you a little trick in a second. So what I did was I took this map, and then I took the same thing but expanded it by 30% and superimposed it on it. Okay, so all I did was I took the same star chart and I just expanded it by like 30%, and then I lined them up so that this blue dot, this galaxy here, was they were all lined up. There was aligned on this blue point. So what you see is this is to illustrate the idea of expansion, right? the expanding this image just by 30% is sort of like expanding of space in the universe. And you can actually see Hubble's law in this, because if I'm expanding space itself, then this points that are close to this center point are moving a little bit away from it, but points that are further from this bright spot are moving much faster away from it. Do people see that? So it's sort of an illustration of Hubble's law. The further away things are from this blue point, the faster they're moving away from it when I expand it. And the other kind of cool point is it helps to understand why, like, we don't have to be the center of the universe in order for this to make sense, because I can line this up with any point I want, and hopefully I can do this. So let's say I pick this. Let's say I'm going to pick this point here as my center. So I'm going to line those 2 points up. Hopefully, if I can do it. So now I've picked this point as my center, and it looks like everything is expanding away from that point.
So Ella asked, like, what is the space expanding into, and how can space actually grow?
That's a great question. And it's a great question that that ultimately I don't have nobody's going to have a complete answer for. But our 3 space and 1 time dimensions that we live in what we know is that they are expanding, so that space itself is expanding. It doesn't have to be expanding into something else. It's just that the distance between things is growing with time. So if you imagine space had some grid on it, actually this is kind of an illustration of that. Now, in this illustration, it looks like I have a sphere that's expanding into some other space, right? But if you imagine you were sort of like a person living on the surface of this sphere, you wouldn't care about the external space. All that matters is that the distance between points is growing. And so from our perspective, the only thing we can measure is that the distance between other points is growing. We can't, maybe there's some higher dimensions, other extra dimensions that this thing is expanding into, but we can't measure them because we live in our 3 space dimensions and 1 time dimension. So yeah, there's a limit to an answer I can give to that, other than to say that we don't know of anything that it's expanding into. It's just that the distance between points is growing, and that's what we can measure. But we don't need an extra thing for it to be expanding into in order for it to expand, because at least our best understanding of the universe is that, as far as we can tell, it's just infinite. So when I double the size of the universe, it's still infinite, but it just means the distance between every point continues to grow. I don't know if that answers your question, or if it partially answers it. We don't usually talk about I mean, there's some physics theories of extra dimensions, but we don't usually worry about it in the sense that we don't. There's no evidence for where those other dimensions would be. So the only thing we have evidence for is that the distance between points is growing, and so our space is expanding. So the reason I wanted to go back to this plot is to say, when we look at this most distant galaxy, we're looking into the past. And so remember, we use this formula here: distance equals velocity times time, right? And I sort of just gave you that formula, and you've presumably seen that concept that distance is velocity times time, or that velocity is distance over time. But that assumes something. If you assume distance equals velocity times time, you're assuming something. Do you know what you're assuming when you write that equation? Oh, okay, we got somebody in the chat. Oh, right, that there's no acceleration, exactly. Right, exactly. So if the velocity, if you're assuming things are just freely expanding with a constant velocity, then you can use that to compute the age of the universe. But we actually don't think that the galaxies have been expanding with a constant velocity, and that actually over the past, since Hubble's time to now, there's been a lot of changing viewpoints on how the universe has evolved over time. So that velocity you might imagine the Big Bang just shoots things out with a velocity, and maybe that velocity stays constant. But there's something in the universe that might, that velocity might not stay constant. One thing you might imagine, and people thought for many decades, is that the universe should decelerate because of gravity, right? All these things are gravitationally attracted to each other. They should be slowing down as they expand. And so for a long time, people thought that that would be true. If you notice, what I did here in this plot is I said that Hubble's constant was 70 kilometers per megaparsec, which is much closer to the established value, and it fits really well with the closest galaxies, but it doesn't fit with the more distant galaxies. Does anybody know why it might not fit with the more distant galaxies?
Matthew said they are slower because we are looking at them in the past and they'll accelerate in the future.
Yes, that good. Very good. All right, you skipped through all of the things I was going to say. Good. So if you look at them further out, they are actually slower than this line because in the past, the universe was moving slower than it is now. So Hubble, what we call Hubble's constant H naught, has been changing in time. So this is your first evidence that that's true, is that if you look far enough into the distance, you're looking into the past and you're seeing that galaxies further into the past were moving at a slower rate than than Hubble's law would have predicted. That means that, and so that implies that the universe is actually accelerating, which is kind of crazy because it's the opposite of what people thought. So this is just something that was discovered in the 90s. Up until the 90s, we never imagined the universe would be accelerating. We always thought it would be decelerating because of gravity. And so actually, the other thing is there's a whole bunch of more data that I had that I didn't share with you, which is if I expand the graph out, you can see much more distant galaxies, and they are moving much more slowly than this Hubble's law. So that means the further you look into the past, the further they are off from Hubble's law, which means they're moving even slower in the past, which means that as they move towards now, things are accelerating. So Hubble's constant had a different value in the past. And so it's accelerating and growing. So this was a shocking result when they discovered it in the 90s, and it was Nobel Prize winning because it was so unexpected. We actually still don't really know ultimately why the universe is accelerating. We know that it is, though. There have been like a dozen different ways of measuring it, and now we are very confirmed that it's accelerating. So it's not only expanding as Hubble showed, but it's actually accelerating. And here's a nice fun plot. Dave, you should let me know when I'm running out of time. This is I'll tell you what the X and Y axes are. This is the x-axis is just time. So this is sort of a theoretical plot. So the x-axis is time, and the y-axis is what we call cosmic scale factor. And you don't have to know what that is, other than it's meant to measure like the expansion of the universe. So you can think of it as like when I expanded that photograph by 30%. That would mean my scale factor was 1.3. And so as the universe, okay, good. So anyway, these three models are sort of old models that we had that we thought the universe would expand and then contract again because of gravity. And so we had all these different theories as to how the universe was expanding. But nowadays we know that it's accelerating, and we don't know why. And when astrophysicists don't know why something's happening, they just think the best thing they can come up with is to give it a name. And so we call it this thing we call dark energy. The actual composition of the universe is there's things a lot of things we didn't talk about, we're not talking about today. There's ordinary matter, which is like the stuff that makes up you and me, the atoms. And then there's this thing called dark matter, which I'm not talking about today, but it's other matter that we're still trying to understand. But then the bulk of the energy of the universe is this thing called dark energy, which is this unseen energy which seems to be causing the universe to accelerate. And we're trying to understand, astrophysicists are actively trying to understand the nature of dark energy and what it is. But and part of that process is getting better and better measurements of the expansion of the universe to understand what is causing this acceleration.
Should I just book you for next month for part 2? I think we're having a really good time here. So, but we are significantly over our time limit, and I know people have to go. So why don't we wrap up here? Let me just say to our students, if you want to be a theoretical astrophysicist, you can be just like Professor Duffell. He's a good role model for inspiring us. I feel like my head is smoking right now from the last 10 minutes of conversation. Anyway, let's wrap up here. Thank you all for being here. Thank you especially, Professor Duffell. And do you have any final comments? We still have questions coming from the chat. If you have to go, anybody that has to go is free to go.
Yeah. So feel free to go. I won't take it personally, but I'm happy to stick around for a little bit and answer extra questions.
Okay, so let's officially say thanks for coming to SMAP. You've heard from a great theoretical astrophysicist. Come to Purdue and study astrophysics. We're here. Thanks for coming. Stick around if you have a question, and Professor will stick around as well. Bye-bye, everybody.
Thank you.
Thank you.
So, Paul, we had a couple of questions come in here.
Yes. So I have one question. I'll give. How many universes are there? I can tell you there's at least one. That's a difficult question to answer. So some people think that there's like an infinite number of universes that have to do with well, some people think of it as a way of interpreting quantum mechanics, that there's different possible universes applying to every possible thing that could happen in the universe based on quantum mechanics. There are other theoretical models that say our universe that's expanding is one of other universes that are also expanding in a larger dimensional space, and that even that those universes, as they expand, could collide into each other. And when I did my grad school at NYU, there was a professor there who was actively working on that and trying to see if there were any way we could observe another universe colliding with ours, which seems crazy, but it's something that there are many astrophysicists that try to do that, and it may seem like a long shot to try to be able to observe something like that, but it's if you did observe it and did really confirm that that's what was happening, you would suddenly be able to talk about universes outside of our own. But for the most part, it's very hard to say what's going on outside of our own universe because that's the one we live in. Isabel wanted to know what I studied. What maybe you can ask in general. So I went to grad school for physics, and I have my research is generally computational fluid dynamics in astrophysics. So what I end up working on is so I do theoretical work on lots of different problems in astrophysics, anything that involves gas moving around. So I have done work on protoplanetary disks. I've done work on supernovae, lots of different problems in astrophysics. But generally, when I went to college, I studied physics. I don't know if that answers your question completely.
Yeah, it does.
Okay.
I just ask that like every single session because I'm
okay. No, that's good.
Study. Yeah.
If you're interested, I also have a podcast that's called the Astrophysics Podcast, where I interview astrophysicists and ask them all about science and how they got into astrophysics.
Is it on Spotify or where?
Yeah, you'll find it there. You'll find it on any of the usual podcast platforms, but it's just called the Astrophysics Podcast.
That's great. Thanks.
I'm sorry, he said posted a link.